is material that is somewhat dense, but it'll involve you working along with me, so we'll get there. But first of all, let's talk about the exam next week. First of all, the exam is on Monday night. It'll start at, well, class will start at normally at 6. We may have some class material and then the test, depending on how long the test turns out to be. I haven't finished deciding exactly what I'm giving this class yet. But in any event, plan on spending your normal class time doing it. If you're one of those people that has an accommodation for something else, you've already contacted me and arrangements have been made. So those of you that, let me see if I can make this window bigger so I can read your names on it. Yeah, there I can. We'll do the same sort of procedure we did in that one assignment. I'll basically have you download your copy of the test. Everybody's test is different. And then you'll have a set amount of time you can work on it. You'll put your answers inside the angle brackets. Of course, we'll go over all this again before we do the test. And at the end, email it to me. Then we'll have a resume time when class will start up again, and we'll verify that everybody actually turned in a text file. You know, I don't want somebody turning in a picture of a duck or something. That's no good. Okay, how are we doing? We're one person short, but haven't we been one person short all along? No, I think last week we actually got up to 25 people by the time somebody drifted in a little bit late. Well, hopefully they'll figure it out. Now, I'm going to hold a review session on Friday night at 6 o'clock. So if you need a review, want a review, just feel like having something to do, feel free to show up in this room. I don't know how long it will be. You do not have to come. It's not part of your grade if you're there. You won't get extra credit if you are there. It's just a review session. If you want to attend, attend. If you don't want to attend, don't attend. And I'll base what we review on people's questions and on things I think you need to hear again before the exam if you're in the review. Otherwise, you'll figure it out. You have a course outline. You can look at the topics we covered. You can check your notes, and you should be able to figure out the sorts of things that I'm going to be asking you to do. If we did it in class, it's fair game. And if it's an extension of something we did in class, it's fair game. For example, we took a code point and turned it into a surrogate pair. But we may not have in class taken a surrogate pair and turned it back into a code point. I actually think we did. But that's the sort of thing that could happen as well. So make sure you're thoroughly briefed on all the material we've covered. Does anybody have any questions about the exam?
Yes. Will we be allowed to use notes during the exam?
Absolutely. I never in my life had my boss tell me to put away all my notes and do a project for him.
Right. So is there a limit to how much notes we can use?
No, but I'd be smart about it. If you get yourself too many notes, you know, or if you're planning on watching a rerun of a video when you get a question on Unicode, you're not going to get it done in the time I give you. You're going to be just exactly enough time to do the exam if you do what the questions were doing. You know, there's no fluff in there to go dig it up. Now, notes are fine. So if you need some notes to remind you what the color codes of the resistors are, what the standard values are, those are fine because you're not going to spend a lot of time. But if you've been copying down everything I've said all semester, your notes are way, way, way too much to pass an exam. You won't know what to look at. So that's part of what you need to do is synthesize down the notes you do have into something that's meaningful. Usually that's why people restrict the number of pages you need. It makes you have to go review and you don't bring in, you know, in a current events class, I had one of the kids who was in the class with me bring in a copy of the New York Times. He didn't finish the exam. You know, he spent all his time looking for whatever the article was the teacher had asked about. So, yes, you may have, it's open book. You can not use another person. That's basically the main rule about it. You can't like get online with somebody in the class and say, hey, I have this question. It looks a lot like yours. Let's work on it together. If you do that, you won't finish. And I also catch you, don't assume I don't have some traps in place. I do. And so, you know, look at all the other students you're dealing with a wary eye. And be very careful that you don't make anything that looks like you're attempting to cheat. I'm not going to make you go through the process of doing that honor thing that they have. That's just way, way too much trouble for you guys, and definitely doesn't let me test you properly. So, I'm going to give you a test. You're expected to use your notes, and you're expected to not talk to other people while you're taking the exam. Just do the exam and turn it in. And you'll be glad you did. I mean, that's the sort of thing that really will put a feather in your cap. And remember, it is 10% of your grade. If you got a 0 on it, you're down about a letter if everything else were perfect. So it's not life and death. But you want to do well because typically, historically, people that do bad on one exam continue to do that. They'll swear up and down they're going to do better on the next one, but they typically don't. Any other questions? Okay, now, there is an outside chance the school will be doing some sort of maintenance on the system at 6 o'clock on Friday night. I don't think they are, but if they do and we don't get to have the session, oh well, too bad, we don't get a session. I don't have any other time when I could do one with you. So hopefully that'll go through, and those of you that want to be there will be there. Remember, you don't have to be there. I'm not giving, if you just do like you do for class here sometime, where you just come sign in and then you come back around 9 and turn off your user ID. You're not going to need to be at the review. So, enough said about that. Let's talk now. Do we have 20? We have 25 people. Everybody's here. That means everybody heard all the good news. Okay, so we're going to talk about VHDL tonight. We're going to extend what we have been working on, and we're going to actually look at some code and learn the syntax of the language a bit. I'm going to leave a lot of it out, because I'm going to give you the part that if you knew it and you went in for a job interview, you'd probably get the job. And they'd have to train you in the other things you needed to know. So pay attention if this sounds like something you'd want to do, or if you want to just have a very rich resume. It's always very good to have a mix of technology in there. If you show me, look at this, I have a certification in some sort of security thing. And I said, well, that's about as good as the expiration date on a can of milk, right? Because it was good when you got it, but certifications change. Computer science gets added to, but the basics of computer science have remained the same ever since I've been teaching it. And I've been teaching it, Lord knows, back to almost to the 70s sometime in the 70s. And so a lot of the material you get now are the same thing we were teaching then. Of course, there's a lot more material now, and some of it's become more refined. Okay, so VHDL. We're making chips. To make chips, we have to design and program them to basically describe what the chip does. This is not the same as when you use a CPU and you write programs which do something algorithmic, and the statements of what to do are given in order. Explicitly how to do it are given to it. Rather, what we're going to do is describe in VHDL what the hardware should do, and then let tooling software, in our case it's going to be GHDL, figure out what that means in terms of what an FPGA would be able to do. And of course, if we had, and we're using more advanced software, we could then pass that design off to that software, and it could fit it and then place and route it inside of a particular chip. Let me bring up a notepad here. There's several stages we're going to have to go through. We talked about some of these last time. But we're going to edit a file. We're going to put the description of a design in it. We're also going to edit a file, which will be the description of a test bench, or some way to test that design we just built. A design that's untested is probably not something you want to build, particularly given the cost of doing some of these things in some of the more expensive chips. You want to make sure you've pretty thoroughly tested the design you made. Now, this is a great thing to know, because on the final exam, not the final exam, on the first exam, if I ask you, for example, to build a state machine, you could then come back and write a little VHDL's description of the state machine, and you could check to see that your equations were right. So this would be a way that on the exam you could actually check a more complicated program by simply putting in a definition of the machine that you want to have, let it run, and then run a test bench against it to see if it gives the correct results. I've had students do that before, usually the ones that succeed, and they have, actually when they're done, they have that big aha moment that says, oh, this really is pretty valuable stuff to know. But anyway, we're going to edit the description of a design, and we're going to then edit a description of a test bench. Then we're going to do something that the big tools typically require plugins for. We're going to simulate the design. We're going to simulate the design by running the test bench, which has instantiated the design. And then we are going to look at a timing diagram, see if it does the right thing. So those are all that's kind of the startup steps we're going to do. We're going to edit and simulate. Now, when we do the edit, there's a couple things we're going to do. One is we're going to check the syntax of our programs we write. That's the -S option in GHDL. We're going to analyze the design. That's the -A. What it does, it basically takes effort, and it actually in real life really runs the syntax checker as well. But what it's going to do is it's going to check to make sure that the syntax is correct, and it's also going to create kind of an executable design that we could then pass on to hardware to create a real chip out of it. In our case, the next thing we need to do is we need to elaborate the design. That's the -E option. What it does is it checks a design to make sure that all of the other designs that it uses exist already. For example, if we try to elaborate the test bench before we've analyzed the thing that is going to be tested by the test bench, we should get an error because we have a test bench and no design to test. So it's a way to prepare in advance what we need to have ready in order to be able to run the test. Then we'll run the test bench. We can't run the design because there's no way for us to change the inputs and outputs and simulate it. We have to run the test bench. That's the -R option, and it's going to have a -VCD or VCD option, which lets us create the timing diagram. And we'll temporarily name it always VCD.VCD just so we don't write over any wrong files. So those are the main steps we're going to do. Once we've done all of that, we're going to check using gtkwave. We're going to put that in VCD.VCD or whatever that is. We're going to check the design's timing diagram to make sure that it's correct. A syntax checker is done against the file.vhdl. Let me call it this way because it's more correct. It's done against the entity.vhdl, and also will be done against the entity's testbench.vhdl. The analysis will also be done against those two files. And the elaboration will be done specifically against the entities. So it would be run against entity and entity underscore testbed in this case. And ultimately, when we run something, it's going to be run against the entity as well. Notice these two, although I'll make the mistake several times tonight, these two are run against the entity specifically. These two are run against the file. It contains the definition or description of the entity and the file that contains the definition of the test bench. Now this leads us to two design things that we need to be considering. One is the code we write may be simulatable. You might be able to simulate it. The code we might be able to synthesize it. And those are two very different things. Test benches always fall into this category. They always have to be simulatable. They will never be put into a chip. To put something into a chip is to synthesize it. That's first step. Second step is something called place and route. And the third step is to do a timing analysis, basically. But we don't have these two. We can do the timing, we can review the timing, but we can't do a thorough timing analysis like we could in a major tool. When we say we want to synthesize something, that means we want to eventually create some hardware out of it. So our entity will be something we want to synthesize. Our test bench will be something we want to simulate with. Now, we will put some extra stuff inside of the entity which allows it to be simulated and simulated property. Here's one of the problems we have. Let's say that in my test bench, I'm creating the AND gate that we looked at last time, and I say A gets changed and B gets changed. What did Y turn into? And the problem is, we know that after I change A and B, Y takes a while to actually have a value. There's an amount of time that it's going to take for A and B to both propagate and become Y. Well, the actual chip description doesn't care about that because the chip is going to do what the chip does. So when we synthesize our entity into it, we have no control over when that's going to happen. We know it's going to be some amount of propagation delays, but really it's going to be up to the tools to make sure that it meets some requirements, not up to us coding some particular time in it. However, to make it simulatable in software, we may decide to code some simulatable only stuff in our entity and just have the synthesizer ignore it. And that's what we'll probably wind up doing. So that we actually then, when we look at the timing diagrams, they're more meaningful because they will take into consideration some potential, for propagation delay, which wouldn't happen. If we just ran it without that, the synthesized design would just simply, but it's simulated, simply immediately produce Y as soon as A and B changed. And that, of course, is not the way the real world would work. Now, for initial testing, yeah, we might leave it alone because it doesn't really matter until you get complicated. But complicated happens rather quickly when you have, a million transistors to work with. So does anybody have any questions about what I've just covered? Okay, I'm going to leave this where I can get back to it again in a few minutes, but go off the screen here if I can. And we don't need anything in here at the moment. So what we're going to do, and you do this with me, is we're going to open up a command window, command prompt. So you do that with me and give me a green light when you've got it open. Okay, it looks like most people were able to do that. If for some reason you didn't do your homework and get ready for this stuff tonight, you didn't prepare, you're going to have to follow along best you can. So make sure you get lots of good notes. A lot of this is best experienced, though, rather than watched. So what we're going to do here is I'm going to CD to my desktop, change directory, my desktop. I'm going to change directory, VHDL, do that 3 times. If I do a directory when I get there, I should be in the proper spot. So you do that as well. Give me a green star when you've gotten there, or green, whatever those things are. Okay, now what we're going to do is, since we opened a new command prompt, if we're on Windows, we have to reset the path so that it includes the tools we need. To do that, I'm going to type the word SET and then hit the Tab key. It should give me the batch file I want to run. Then I'm going to push Enter, and it should run. To test that it ran, type GHDL --V. Give a couple seconds, and then it'll come back and it'll tell us what version we're running. I'm running 0.34 development version, last updated in 2017. I know we're going kind of slow here, but we've got a couple people that are getting a little behind, so I'm trying to drag them along with us here. The other class had 100% participation, and every single person in the class had prepared. Every single person in the class was able to keep up with what we were doing. So I was quite pleased with them. They're right now, I'm not sure they're my favorite class because I got a lot of people in here that I think are doing a really nice job, but they're pushing it. They're trying to get there, that's for sure. Okay, so we have GHDL. The tool is ready for us to run. We have some base programs to look at to learn the syntax down in a directory called work. So change directory to work. I'm going to clear this off my screen by doing CLS, which stands for clear screen. Then I'm going to just do a directory to see the files that are in there. Now, we did some stuff last time. You may have more files than me because of, we ran a couple things and we did a little, so that was actually on Monday night, wasn't it? That wasn't last week, that was on Monday. What we're going to do is we're going to start as though we have a clear thing. If I do a VHDL-D right now, sorry, GHDL-D, that's my other mistake I like to make. I have nothing in there. So we need to make yours the same way as mine. So type GHDL-C for clean, and then do another GHDL-D to make sure it really is empty. If everybody has an empty work file now, give me a green light. Well, I'm making you guys participate tonight. Okay, so what we're going to do now is we're going to take a look at some of the source code and start to look at how you write this stuff. So we're going to do a notepad of and_2.vhdl. We'll bring that open in a window. Mine will probably have a bigger font than yours, but that's just because I make it big enough that hopefully everybody can see it. Okay, now let's talk about what we're looking at. Remember, this is not the same as a C program. What we're going to see in here is going to be a description of what needs to be done, not a how to do it. There's no recipe in here. Generally, inside of a VHDL file, there's going to be 2 or more sections. One of the sections is called an entity. The other section is called an architecture. There may be multiple architectures because you may describe the chip in different ways. And if there is, there'll be a third section called a configuration section. We're not going to worry about that. We're going to make one entity with one architecture, and just make that the gold standard. Lots of times in the real world, you'll find that that's really what's done. Well, there's a lot of fancy things you can do. Most of what you do is the basic stuff. The fancy stuff sometimes just gets you in trouble. It isn't really what we needed. Now let's talk about how these are kind of divvied up. We say the entity has a name. This name, we're going to, as convention, make it the name of the file. See, and_2.vhdl. So the entity name and the file name are paired together. And we're saying this entity is the following. It's what's inside the thing here. And the entity's definition ends right here. And we once again use the name so it's very clear who we're pairing this end with. Now, inside the entity, what we're going to describe are the inputs and outputs. Very basic stuff. There are other things can go in here, but for our purposes, just the inputs and outputs are necessary. And the inputs and outputs are called a port. And the port we have is going to describe by name, in our case, 3 variables. Or these are actually external pins relative to this entity. They may not physically be external pins, but you can think of them as the way to get to the outside world. They're going to be the things that the test bench talk to, which is why we can't run this by itself, because we'd have no way of talking to these input and outputs. A colon, and then we say whether it's an in or an out. There's a third choice we could put there, which is the word buffer. And a buffer means it can go in or out. And we don't have any of those in this design. Then we give the type of data we're using. We're using something called standard logic. Standard logic is defined in this header that we included up here. We included the standard IEEE namespace, and from that, we pulled out standard logic 1164 and all the definitions that are in there. One of those definitions is standard logic. So we didn't really need them all. We could have just gotten standard logic, but because we're going to use standard logic vectors also, it's better just to pull them all out. This also is more traditional. This also is what many people do when they're writing in Java or in any language that use those imports, and they need everything. They just use a star, and then they let a tool like Eclipse figure out which ones they really needed. But in our case, this is the inputs. Now, interesting aside here, that semicolon, is that a separator or is that a terminator? How many people think that's a terminator? Give me a green light if you do. And the answer is you would be right. That is a terminator. Is that a terminator or a separator? If you think it's a terminator, give me a green light. This one, amazingly, is a separator. This one is a terminator. This one is a terminator. We know this is a separator because it separates 3 items, and the last one doesn't have a semicolon. So a different use, and if we were to look at the, basically the regular expression that handles compiling these, it would make a difference between whether or not this. It's wrong to have a semicolon there, but you're not terminating, you're separating, and there is no more. So that's just a little side fact to know and tell at the dinner party when somebody says you don't know anything about VHDL because you had 1 night on it. We had 2 nights. You guys are experts at the end of 2 nights. I've had jobs where we had to come in and learn a language in less time than that. Okay, so this is the way you describe an entity. This entity is going to be simulatable only because of the fact it's going to be called by a program that was written to be simulatable. There are no features in here right now that would keep this from being synthesizable. This can literally be put into a chip. I'll show you in a second how we're going to change it so it's also simulatable, and the synthesizer will ignore the fact that it is. Second section is called the architecture. It describes the chip, basically. we've described kind of what the interface is to it. You can kind of think of this as a function, you're going to call and that definition inside of a program. This is the input outputs and their types. And you could think about that if it helps you a little bit, but don't get too much caught on the software programming sides of things, because there are enough differences that you'll write bad code if you follow your software practices. Now, architectures have a begin and an end. The end is for the architecture, not for the begin. There is no end for this begin. It's just everything that follows that down to here will be the end. Now, although this one doesn't have it, the section right here is used for declarations. And after the begin, we basically have things like this, which are called concurrent signals or processes. Now, I will also tell you that a concurrent signal is actually really just an abbreviation for a simple process. Now, if I had a second output, let's say I had an output called Z, and maybe I took B and Y as the function. Both of these are concurrent signal assignments. What that means is, in the real chip, they're always doing what they're doing at exactly the same time. I mean, whatever A and B is, whenever it is changed, Y will change. Whatever Z is always whenever B or Y has changed to something else. So we think of these as running completely in parallel with each other. This one will run while this one is forming Y and get a wrong answer for Z if Y is just getting ready to change. So by doing this, we care about propagation delay, because the Y he's going to see is going to be perhaps in our TTL 22 nanoseconds late, meaning Z will change 22 nanoseconds after we might have expected it to, certainly with respect to when A changed. But the simulators know to repeat these over and over again until there are no more variables changing before they go back and try to do them all again. The other thing that is of note is that right here, Y has changed and is available to this statement only because these are being run concurrently and only after Y has really changed. So we're going to see later, inside a process, these two statements are not run concurrently, they're run sequentially, and this Y is not available to the next statement. It's not available until it falls out of the block that it's in. So it's a very, very different thing than thinking of those as being, just an assignment statement in some C program or Java program somewhere. Okay, I've changed that, so let me go back to what you all have. Now, we're going to add one thing here to this. We're going to say after 100 space ns, after 100 nanoseconds, that's when that'll actually make Y be equal. So we're adding some code that's not synthesizable, but is simulatable. On the real chip, this will happen in whatever time it takes. And it may vary. It may take 50 nanoseconds, it may take 10 nanoseconds. Different chips may have different values. But for our testing, we need to give some sort of value if we're going to get meaningful timing. So we're going to change this to say after 100 nanoseconds. And that's realistic. That's in the ballpark of how one of these might actually change. Probably 10% of that, but nevertheless, it'll give us enough to see in the diagram. So make sure you save that. Now I'm going to make a mistake in here. I'm going to get rid of this. Don't you do this. I'm going to get rid of the space that's there. Save it again. I'm going to run out here. I'm going to say GHDL-syntax check AND_2.VHDL. And it's going to come back and it's going to tell me on line 20 and around column 31, a space is required between the number and the unit name. So I can generate syntax errors by typing bad syntax. I can get rid of this semicolon here. Run it again. Semicolon is expected instead of the word architecture. And we saw architecture instead of the semicolon, so let's fix it. Now, yours and mine should match exactly. Do the same thing again. GHDL, you do this, GHDL space dash S space and underscore 2 dot VHDL. Okay, now, GHDL-D will show you there's nothing in the work file. We would have to run the analysis for it to get there, but we're not going to run it. We're going to make a mistake in the future when we needed to have run it and didn't. So I can show you something. So we know the syntax is good. What I want to do now is look at the test bench for this particular piece of code. It's going to look very much the same in terms of the structure. So it's called and underscore 2 underscore TB dot VHDL. Everybody could type that? Open that file, and when you have it open, give me a green light to tell me you got it. Oh, you guys are good tonight. I don't know what's going on here. Okay, we're going to look at this file. First thing we're going to notice is we have two sections. We have an entity and an architecture. The entity, however, contains nothing. And that's correct because we can't pass anything to a program, so the test bench has to be able to run without input. And since it creates no output itself, this is never going to be put in the chip. We're simply going to rely on the fact that it also creates a timing file for us, the vcd.vcd, to look at what it did. So here's our architecture test of and to testbed. It always points back is, and here's the architecture. And the architecture runs quite a ways down to the end test. In the middle of the architecture, you're going to see there's a begin. That's the one we saw a while ago that I said above it, there's going to be some declarations, and below it, there's going to be the architecture itself. Let's go back and start at the top and look at the declarations. First of all, we say we need to know about a component, and the component we need to know about is the and to component. Here's the end of that component definition. I guess all these really should be indented because they're part of the component. And what does the component have in it? Well, it has a definition of that component's interface. This is very much like, again, you're putting an include file in a software program, defining the functions you're going to call and what their inputs and outputs are. A component would be like a class definition of something you're going to later instantiate. We're going to create an and2 and test it. And2 by itself is just a description. We have to create one of these components to actually test it. This is literally this. It's exactly that port definition. It's copied here. So that's how we describe we're going to somewhere in our program, we're going to create one of these. This doesn't create it, it just says we're going to. And here's what it's going to look like when we create it. Then we need some work things, and we call those signals. We have three of them, S1, S2, and S3, and they're of type standard logic. Notice we don't say in or out because they go both ways. These three guys are inputs and outputs. They're what we need them to be. Here's the begin we were talking about. And the first thing we're going to do inside of here is we're going to instantiate this guy. To do that, we just make up a name. A2 sounds like and2 a little bit. Give it a name. We don't need that part usually, but some compilers require it. We say and to because of where it is. It's after the begin. That means instantiate one of these. And by the way, we want to map your A to our S1, your B to our S2, and your Y to our S3. So this statement is basically the same as just a process that is simplified without the word process, and it runs concurrently with everything else. So it's going to run constantly. Anytime A changes, S1 will change. Anytime B changes, S2 will change. Anytime S3 changes, Y will change. So we simply map them to us. And this runs constantly. And what does it do? Well, A and B are hooked to an AND gate. So whatever A and B are, Y will be the result. So this is going to take care of setting S1 and S2. AND gate will use those as its real inputs and then return to us the S3 we needed, which is going to ultimately be assigned to Y from the chip. So here's our process that's going to be used to make this happen. Now remember, concurrent assignments as well as these port maps, each one are considered processes. They just don't use the word process because they're one-liners. However, we're going to also create a testbed process. It's a process. Down here the process ends. Which one? Well, testbed process. And here's a begin inside of it. Processes have a begin statement. Above them would be anything we would declare. Below them are what we want it to do. Now, the things that are down here are strictly non-synthesizable. These, in terms of particularly the weights, the S's are actually synthesizable but would be useless to us. So what this says is, use a sequential assignment statement. Notice how it looks exactly like a concurrent one? We know it's sequential, though, because it's inside a process. Set S1 to an X, set S2 to an X, wait for a nanosecond. Now, when I set S1 and S2, these guys are getting changed, which means the A and B on our port are producing another Y, which is assigned to S3. In our timing diagram, we can look at S3 then and see what actually the answer was. Wait for a nanosecond. Do it again with different values. Wait. Do it again with different values. Wait. Do it again. Wait. Do it again. Wait. Then when we're here, if we fell out the bottom of the process would be re-executed over and over and over again. It would continuously be executed. So we need some way to stop it. And to stop it, we simply wait. Now, there's two ways for processes to be defined. One is including wait statements. The other way is with some parentheses and some variable names after it, and that's called a sensitivity list. In a sensitivity list, if any of the variables in the sensitivity list change, the process runs. In our case, though, since we use weights, we can't use a sensitivity list. If we use the sensitivity list, we can't use weights. So they're mutually exclusive. But at the end here, we threw in the special wait, which is simply wait forever. And since we're on the first pass through the process, we'll never be able to come back and do the second pass through the process. Now, there is one bug in this based on our code we wrote over here. I can tell you that it's in the process. Can anybody tell me what it is? Turn on your mic and tell me if you see it.
The one on the left tells you to wait for 100 nanoseconds after A and B, while the one on the right doesn't.
That's exactly the problem here. The problem is that this is kind of a standard way of writing it if you know you're not going to check timing. But the moment we put the timing in over here and made it realistic, this is no longer realistic. A realistic time would put this, instead of nanoseconds, into something like microseconds. So you do this with me. Edit, replace. And in the thing, you want to replace NS semicolon with US semicolon and do a replace all. NS semicolon replaced with US semicolon. I go look again. Now, this is going to happen every microsecond instead of every nanosecond. And there's 1,000 nanoseconds in there, so we got plenty of time for it to do its thing. So that's a change. We'll have to do that to all our test beds because I'm sure I use nanoseconds in all of them. So, file save this. Give me a green light if you're caught up. I swear we got a different bunch of people in here tonight. Okay, what we're going to do now is we're going to check the syntax, just in case we did our replace wrong. GHDL-syntax and _2_tb.vhdl. My syntax was good. If yours isn't, fix whatever the syntax error might be. Now we're going to analyze this file, GHDL-A and _2_tb.vhdl. And do a GHDL-D. You'll see that our entity and our architecture are now in the work library. Now, however, when we elaborate the test bench, it's going to try to find that AND2 entity, and it doesn't exist in here yet. So we're going to do this, and this will cause an error message, -E, and we only put the entity name here, AND _2_tb. We want to take the entity that's in the work library and try to connect it with any other entities that it needs to instantiate. It's going to come back and say, can't be done. This thing you're trying to instantiate, which was the A2 guy, isn't bound to anything because of the fact, if you look, it's not in the library right now. So we'll get it into the library. We'll do a GHDL-analysis or analyze and _2.vhdl. We'll put it in the library. Now, it itself doesn't use any other things, but it's good practice to go ahead and elaborate it anyway. And again, we'll elaborate its entity. And then we'll go elaborate the test bed again, and _2_tb. And this time it runs without an error. So give me a green light there if you're caught up. Okay. Now, in order to test, we could do this. You don't need to do this. GHDL-run and _2. We could run it. It wouldn't do anything, and it doesn't create any timing diagrams or anything, so it wouldn't be a useful thing to do. We could test it by building a chip, and then you'll put the chip into a circuit somewhere and apply signals to it. So we could do it in a real way as opposed to a simulated way, but we can only simulate because we haven't even told this thing what chip to fit it into yet. We just know that it can be an FPGA. So what I'm going to do instead is I'm going to run the test bench. But again, it's not going to give me any output. So I need to put in the VCD flag and then put it into a file. I'll call it vcd.vcd just to be safe. And I'll run that. Now, if I were to look at, if I said notepad vcd.vcd, where did it go? Oh, it's on my other window. I would get this really cryptic file, which is all the timing information that GTkwave knows how to read. So it'd be possible for you to sit down and actually write code that could, do a better GTkwave by getting these files from something like this. We can read some of it. Here's the time and date and version number we use. This, I think it's version 0. I guess it was 0.33. Here's some variables, that's S1s. These are the names we saw in our program. There were their definitions. And then here are the actual events happening at some particular point in time. Don't know what that all means yet, but we'll find out. I can guess that this was at tick 1 and this is at tick 100 more than 1. This is a tick 2, and here's tick 100 more than 2. So we're seeing something change and then the output going somewhere. These other little marks, who knows what they mean? They look like special symbols. But in any event, we could come through and look at that. But it's easier to have a program that can do it for us, which is what gtkwave does. The gtkwave, vcd.vcd. You may get a splash screen, you may not. You may not see my splash screen, actually. But in here we have, first of all, the name of the component that's inside of our project and the 3 signals we have. If I click on that, I'm going to see the actual signals for the component as opposed to what our internal signals are. So the more interesting one to us is actually S1, S2, and S3 because they're the signals that represent what we would ultimately ourselves, if we had had a port, put on the output. So this is the test bench's highest level signals. So we can copy these one at a time over here. We also, although it's painful to do because they didn't get the UI right, you can click on that, you can hold Shift down and click on the bottom one. And while still holding both down, the mouse and the key, you can drag all 3 over and release them. Or you can do them one at a time. In any event, they're all over here right now. Now, I gave you a key combination, which I believe is Alt-Shift-F to make it fit, but you also can come up here to the magnifier on the left, the one with the little square box in it. Click on that and it'll make it fit. Now, we can click anywhere in the window and we will get a red line. That red line, if you look over on the left, will be decoded to be the values of the signals. So XXX seems reasonable. Interestingly enough, if you notice, there is a 100 nanosecond delay where not only is this X, but it's undefined. So that signal 3, didn't even receive a value until that 100 nanosecond time was gone by. Notice that all of the signals where there's a change in the last line, which is basically our output, are delayed by 100 nanoseconds. So if we were looking in that little window of time right here, we would see A is a 0, B is a 0, but Y is undefined. Interesting. We can move this over here. 0, 0, 0 produces 0, 0, 1, 0 produces 0, 1, 0 produces 0, and 1, 1 produces 1. Again, we have a little window of time here where we get a wrong answer. That is a glitch or a hazard. We'd have to make sure we never looked, except when the data was stable, after it had time to fully resolve. That's why a test bench is so important. And that's why it was important that we make our actual device simulatable, even though it's not synthesizable. We have no idea what it's really going to be, but we're pretty sure it's not going to be as bad as 100 nanoseconds. Anybody have any questions about what we just did?
I got like a little lost when you were going through, but basically, when you have the gtkwave up, could you make sure that your command prompt is still visible so I see the steps you got to get there?
I probably can't find it right at the moment, but it'll be back up in a minute.
Okay.
Your notes from the other night have that step in it. Now, if we leave the red thing where it is, we can use the plus magnifier to zoom in, which will exaggerate this time. If we want to, we can click very close to that signal, and without raising our finger, we can drag across. While I'm moving, if you look up right above where my cursor is now on the white bar, you'll see there's a time changing. The first time is where are we in the entire file, where it's some number of picoseconds in. And the second one is where is the cursor relative to the other cursor. And so, no, sorry, I got those backwards. The marker is this guy. The cursor is where is the cursor in time. But if we look at this, we'll see that this little green rise here and the other one have 101,700 picoseconds different. I can't release that and leave the number alone. You have to have your finger down in order to and make it have two cursors. But now I have 101, 200. That's very close to 100 nanoseconds. And the error is just in the fact that I'm not exactly sitting on those green vertical lines. So if we ever wonder how long a time is, we can measure it using the dual cursors. I can also shrink it back down so things fit. So if I kind of wondered how long is this period here and I couldn't see 2 to 3 microseconds up there, I could grab close to that and close to this, and my marker would see it's about 1,000 nanoseconds. And of course, 1,000 nanoseconds is going to be close to 1 microsecond. Now, the biggest problem we had is when we opened this initially, things were in femtoseconds. That's why we had to fit. A femtosecond, if you think about it, if we go way back to our web page, we go to prefixes, is 2 to the minus 15th. It'll be down here. So we have milli, micro, nano, pico, femto, which means if I were to write that out just as a number, the initial delta of times we're working with, we're not milli, we're not micro, we're not nano, we're not pico, but we're femto. That's a small number of seconds. So that's why when it initially opens up, we would probably have to manipulate the window we're looking in a little bit to be able to see what's going on. Of course, you always can check here if you have a strange number you don't know. If somebody says femto, 10 to the minus 15, that means there are going to be 5 sets of those 3 zeros. Okay, so let me dig and see if I can find my console here. Here it is. So basically what we did, let's go through the steps just so it's very clear. And this is the full thing. GHDL dash syntax check and to, actually I'm going to use a different file this time. I'm going to use or2.vhdl. We're going to syntax check that guy. GHDL syntax check is testbed. We're going to analyze or2.vhdl. We'll analyze his testbed. We're going to elaborate or2, no VHDL on this guy. We're going to elaborate or2 testbed. GHDL run or2 testbed. Putting our VCD file into vcd.vcd. Anybody, if you have a question about that, throw up a red circle right now. Okay, Ethan, what's your question? I can't hear you.
I was confused with someone for a second, but I answered my own question thinking about it.
Okay, great. Good. Okay, so I'm going to run that. VCD.vcd now should contain the result of running an OR2. Now, we'll look at the timing diagram before we look at the code. So gtkwave, whoops, VCD.vcd. If you look up at the top, this is going from 0 to 5 nanoseconds in terms of, we know that's the actual time we have. But the machine right now is set up to show 1 femtosecond, 2 femtosecond, 3 femtosecond. And if you notice, if you look really close, that's even divided into some number of units. I can't, it's too small for me to count, but there's at least 10 of those there, maybe even more, which would be subunits of femtoseconds. Now, I'm going to drag all these, but this time instead of looking at the S's, I'm going to look at the actual subcomponent. I'll drag all 3 of his things over here. Whoops, see, I raised my finger too quickly. Drag them over, drop them in. Make them fit. And indeed, this looks like an OR equation, right? Everything's set to X's, all zeros, and everywhere else, at least one of the A's or B's are a 1, and the answers are 1s. So that looks very much like an OR function. I'm going to close that for a minute. Now I'm going to notepad OR2. Oh my goodness, I'm talking in some foreign tongue there. OR2.VHDL. Okay. What changed from the end is this name, and it was architecture of OR2. And then, of course, the only thing we changed down here is this is an OR statement instead of a AND statement. So, I mean, same code, you could, if you were writing this again to do some other function, it's really easy. Mostly you copy this code and you change those 6 places, whatever it was. But in the diagram, I noticed we didn't do, after 1 nanosecond. Let's not make it 1. Let's make it be big like the other one was. It's easier for me to measure with my giant mouse here. So I'll save that. We'll come back over here. GHDL dash. Now, I need to analyze it again. I don't need to elaborate it on Windows. I've been showing you that step because you would on other things. I'll leave it as it is. But then what we need to do is we do need to elaborate the test bed again so that it picks that up. And then we need to do a run, GHDL-run, or to test bed, putting the output in VCD into VCD.VCD. I'm going to do a gtkwave of VCD.VCD. Drag my signals in, make them fit. Oh no, that's not the right output for an OR statement. What the heck is going on here? I see some things here, and I see it making its thing happen at 100 nanoseconds. Maybe if we zoom in here somewhere, we'll be able to figure something out. Well, there's my 0, 0, and it became looks like right there at the very last instant, Y finally turned into a 1 because of this 100 nanosecond delay. Give me a green dot if you know what the problem is. Well, I'll give you a clue. If we go way over here to this side and we zoom in, we'll notice that our signals are changing every nanosecond. We also saw that our propagation delay through the chip is 100 nanoseconds. That means we've changed all the inputs and outputs long before the final answer makes it to the thing that's changed. What could that possibly mean for us? That means something must be wrong with the test bench. Because all we did in the code was we simply, okay, well, this is the AND test bench. Let's see. Me finding my console is not always easy. So let's just notepad that guy. Notepad OR2 testbed.vhdl. You do that too. Now, although this compiled correctly, it had no syntax errors. It also seemed like it did the right thing when we ran it without adding propagation delay. There's some changes. Of course, we could steal this one. Well, if we had a different function also, we could just change OR2 to whatever, if we did a XOR or something, change it those 3 places and here. And then where we instantiate it, we could change it. We basically could plug in the other code. So what is wrong with this code? I'm changing it X's to 0, 0, 1, 1, 0, 1, 1. Who wants to tell me?
For in the test bed, we're waiting for 1 nanosecond on each of those lines. But if we remember back at the actual entity, we said wait for, what was it, 100 nanoseconds?
That's exactly right. Remember I said earlier we needed to change this in probably all of our test beds? So in this file under Edit, you go to Replace, change NS semicolon to US semicolon everywhere. And if I do that, now it's going to be in microseconds. I'll save this. I'll close this. And I will rerun the, let me actually rerun the analysis of the test bed. The analyses are of the file. Elaborations, however, are of the entity. So now we can do the run. By the way I'm getting those commands back, in case you haven't figured it out yet, if you're jumping around between commands I've already typed, I'm using the up and down arrow. It saves the history for us. So I'm going to rerun this. Now I can do my gtkwave again. Go into it so that we're looking at the ABCs or ABY signals. Drag them up, shrink them in, and there we've got everything back again. And if we look right in this area here, zoom in on it, we'll see now we've got a proper propagation delay showing. So you see those sort of things. You can even find that you have bugs in your test bench. Don't always assume that the test that you're testing your chip with is got completeness to it, nor that it's going to be proper given some of the timing constraints and things you can add externally that it doesn't know about. It obviously should have failed if you tried to put a chip in that had a 100 nanosecond delay. It should, and that would be correct. So the failure was correct if this test bench should have been running every nano and the chip had a propagation delay of 100 nano. You'd want that to fail. That means you're mixing probably a really fast new technology with some old clunker chip that isn't going to be, useful to you. Okay, let me close down some of these windows. Keep that one open for a few minutes. Now, if you notice, ORs and ANDs were pretty close to each other. What I want to look at now is, let's do a notepad on and_4.VHDL. Oh, not note. Okay. Two sections. We have an entity. We have an architecture. We have the name and4. Now this is going to be a real chip. This one is not directly simulatable. We have to use a test bench to simulate it. So any times we add will have to be added in here in the appropriate spots. Now, the port consists of 4 inputs, A, B, C, and D, and 1 output. So that's the way we would design an AND gate that had 4 inputs. The only time it should be true is if all 4 A, B, C, and D are true. As its architecture, the architecture has a begin, afterwards of the implementation, before it are the declarations. Oh, this is interesting. Look, we're going to use a component to do this. We're going to, instead of implementing in a second here. Instead of us implementing something that looks like this, because this is what the chip actually is on the surface. Internally, what we're going to implement is going to be this. So this would be A, B, C, and D. And then this over here would be our Y. We'll put some sort of intermediate answer in here. I don't know, call it, I don't know, they'll have some name. Just call them R and S. I don't know, making up names. I'm using initials I wouldn't have normally used because that's like for a flip-flop or a latch. But I didn't want to use E and D here, or E and F. So if we could take our already built and tested and working 2-input AND gate and instantiate 3 of them and wire them up in this order, we would have this. We would be really cool. We could order off of the adult menu at Chick-fil-A. Okay, so how are we going to do this? Well, we're going to need to describe an A to a single. We only have to describe one of them because they're all the same. We have an A, a B, and a Y. We're going to have 2 intermediate signals, S1 and S2. So I guess in that picture, this is really going to be like S1 and S2 internally. It'll be just signals we keep to represent those intermediate answers. And then we're going to create 3 of them, 1, 2, and 3. We'll call them A, B, C, D, and the one that generates the Y out. So A and B is a mapping of one that's been instantiated where we take the AND2's A and map it to our A. So our A sits up here. We're going to take the AND2's B and map it to the B. So the A and the B here are the A and the B up here that are passed into us. They're going to be given to this AND2's A and B inputs. It's going to produce a Y, which we'll assign to S1 as an intermediate answer. Then the 2 other ones will be hooked to C and D. So the A on some other AND2 gate will be hooked to C. The B on it will be hooked to our D. Its Y will be hooked to signal 2, the intermediate answer. Then we'll take a third one. We'll hook the third one's A to our S1, the third one's B to our S2, and the third one's Y to our Y, which of course is the final answer we should see popping out. These all 3 run in parallel. They're constantly running. As long as their inputs have not finished, they're constantly running. So if anything changes, they keep doing their thing, and they do it right away. There's no clocking going on here. This is immediate. The only thing that would be affected is when does it happen? But we can't add on this a propagation delay. We can't say after. But we don't need to because these guys are running an AND2 internally, which already has a propagation delay. So this guy, it looks like he's golden. Let's look at his test bench, because his test bench we know minimally is going to have something wrong with it, and that's going to be the timing. A notepad and for tb.vhdl. And very much the same as what we saw earlier. It is going to have a component of an AND4. It never instantiates the AND2 because the AND4 takes care of it for us. We're going to change A, B, C, and D and create a Y output, which we'll have timing for. Intermediate-wise, we need some intermediate signals, S1, S2, S3, S4, and S5. And we'll port map the AND4 that we just defined up here so that its A becomes our S1, its B becomes our S2, its C becomes our S3, its D becomes our S4, and its Y becomes our S5. This runs constantly, and at the same time, so does this. This is a process where we set each of the 4 inputs, and they get distributed to the correct things internally. And then we wait for 1 nanosecond. We do all 16 combinations, and then finally await. Actually do 17 because we have this X thing at the beginning. This won't work right now because of this. How do we change it? We go to Edit, Replace. We change NS semicolon to US semicolon. We'll replace all. Take a look to make sure it changed. It did. We can go up here and go File, Save. Now that's a very interesting concept here. We use some pre-existing hardware to create some other hardware. It would be no different than if we'd created a circuit board which contained a, 3 AND gates, and the big circuit board was packaged in a package, so all you could do is see its inputs and outputs. And of course, inside of something like a PLD or a FPGA, that's the whole thing, is what we're building turn out to be synthesizable items which can be hooked up in various combinations to create larger and larger entities until the entire physical chip has its pins defined and can be used in a bigger circuit. The test benches would never be put into the FPGA because we have real pins that we can hook stuff up to. But in this case, we need to do some things. So think ahead, what are we going to do here? Well, we're going to do a GHDL. Let's do a syntax check because I did make some looking at it, and for.VHDL. Another syntax check of and for testbench.VHDL. VHDL.analyze and for.VHDL. GHDL analyze and for testbench.VHDL. Can you see why I wrote that do-it.batch file? It's because once you get all these things and you understand them, then you just run the batch file and it does all these steps for you. Now at this point, if I do a GHDL-D to display it, I should see that all of that stuff is it now in, well, the AND4 is at the top, is in the work library. So now it's elaboration time, GHDL-elaborate, and for we elaborate the entity, not the file. GHDL.elaborate and for testbench. And finally, we can run and for testbench, putting its output in the VCD file. If I double check that you got everything typed up to that point, and when you're brave enough, hit enter. I think I'm brave enough. Now, gtkwave, VCD.VCD. We got more inputs and outputs now than Carter has pills. If I were to open up this A4 thing here with the plus sign, I would see the 3 things I instantiated. So if I were testing deeply, I could just highlight each one and its 3 signals would show. So I could very closely drill in if something was not working right. If I do the entire A4 component, which is what the test bench has instantiated, remember internally A4 instantiated the other guys, I get all of my signals plus my 2 internal signals, the intermediate answer, and Y. What I want to drag over to the right are the A, B, C, D. Looks like I only got the first 3. I'll drag D separately. And I want to drag Y over there. I don't care about the intermediate answers particularly. If it's broken, I'll care. But let's zoom in. So we'll use the zoom to fit, or you can type the keyboard sequence. What we should see is that all the way at the end, the last one is the only place where a 1 occurs. And it's only when everything else is a 1. All the other combinations in here should give us, zeros. And they do. That's what the answer says. Now, if we go to that spot right where I am right now, and we zoom in, what we'll see is here is that propagation delay that we saw earlier, or we actually built in. Let me actually click there and then pull across. And it's approximately right now 199 nanoseconds. That's almost 200. That means there's 2 propagation delays in there. Now let's think, and I'll throw this up as a hint, why in the world, if I did that, here's A, B, and Y, why do I see a 100 nanosecond propagation delay here, but down here I see a 200 nanosecond delay? Anybody want to take a shot at that?
Because it has to get from the beginning of the first AND gate to the end of the first AND gate, and then from the beginning of the second AND gate to the end of the second AND gate. So you add it up.
So what you're proposing is it takes the 100 to go here.
Yeah.
And 100 more to go here. And those added up together, as you said, equal to 200. And that's exactly right. So if we were to look at the intermediate answers, I'm going to pull them up. And we'll zoom to fit again. And we look like here, and we zoom in. Actually, let me go right there and zoom in. You notice here that between that edge and this edge right here, we have basically 100 nanoseconds. That's because from here to here, for these intermediate answers, is 100 nanosecond delay. So you can see why timing becomes a very, very important thing to have to deal with. And it becomes extremely interesting to try to design around worst case timings. I mean, you think computer science is fun when you're just sitting there writing programs that can, make asteroids get shot with, rockets or something. Well, that's fun. But man, that would be really cool if you could design hardware that could, shoot asteroids out of the sky. And you had to worry about propagation delay, or else it shoots a little early and blows the top off your rocket. Oh well, we'll worry about that on a different day in a different class. Okay, so that seemed to be like it worked pretty successfully. There is one other example that I have in here for you to kind of go through on your own. I'm going to go through it here with you. Where is my Control C happening? I get hitting the wrong key and I'm closing windows right and left, but not the right one. In here we also have one which is called, not FOT, that's my hands on the wrong keys. It was called and/or for, yeah. I'm not going to go over this one with you more than just to point out to you that the real difference in this one is we, in our architecture here, have defined 2 components, an and an or. And then when we instantiated them, we instantiated 2 ands, and we had the result of those go through the or. So basically here, if I were to draw a picture of that, we had, whoops, let's drop another one in. We have 2 ors that we, whoops, what button did I hit there? 2 ands, I'm sorry, that we needed, but we also, as our third element, created an OR gate. And this could turn out to be pretty handy because this is basically the internal structure of an FPGA, right? Things ANDed together, ORed together. Of course, we always build them as NOTs so that we could use a single external gate, but when you're programming them, you might as well use what the device has in them. So this is a very powerful thing. We were able to produce a sum of products type of device. Now, yeah, it takes only 2 things ANDed, and ORs them together, but a lot of small problems can be solved then with this single chip. I'll let you go through building this. I'll let you go through building its test bench, looking at its output, and all will be well with the world. If I type do it, it'll basically run all of the things that we've done, plus an additional one we may or may not have time to look at tonight. So what I'm going to do is I'm going to open up in the GTK wave the Or was it and or 4? But we have, yeah, I'll probably call it and or 4.vcd because with the batch file I can make sure I got the right names. That must not have named it. Oh, it had Testbench in it. And I come over here and I look at the same things I was looking at last time, which is basically A through D, which is basically A through D. I guess I'm not going to get that done. I think if I do nothing else, I'm going to join this project and rewrite that interface for them. Now in this case, oh, I forgot to change that. We know what that is. I forget who it is. Nicholas that keeps answering that question for me. We know that I've got the wrong timings on this. That if this is the and/or guy, he doesn't need to change anything in his signals, but the test bench does. So we'll do that while we're here. And/or 4 at VCD, that VHDL. I'm going to trust that I wrote it the same way. Which who knows if I did or not. What's it doing here?
It's not the test bench.
Oh, that is a good reason for it not to do it. We're telling what I changed with that. That gives you some more fun to debug later if I made a mistake. And because I'm lazy, weep. I can't do it here. I have to use the up arrow. I used the Linux during the day that I don't always remember all my commands. Shame on me. Having fallen forth before, I'm not going to try to do it one at a time. Oh, I got B in there twice. If you get one in there twice, all you got to do is highlight it, right-click, and say delete. If you're really fancy and you want Y separated, you can click the one above where you want a space, right-click, and then see either comment or a blank. I usually put a blank. Then I'm going to make it fit. This looks more like the right data. And we'd see propagations and things occur. You'll see Y is more interesting now because it's going to be turned on anytime A and B are on or C and D. C and D is on, C and D is on. All the remaining one here, A and B, have already been turned on, except for this one, which C and D is turned on for. So it does what it's supposed to do. It'll give you a little code to look at that's somewhat interesting. Now, I'm going to show you, although we're not going to spend much time looking at it right now, something just to ponder. Was that not the name of it? Push it under 4. This thing runs a shift register, and the shift register produces an output, which is the bit being shifted out, plus it takes a new bit in. There's a clock and a reset, which allows me to show you that in a process, you can actually have an if statement. The syntax of which you can just look up if you ever need to use one. But this in particular is treating reset as a special signal. Up here, remember I told you earlier they could have following it a parenthesis and what we call a sensitivity list. This says run this process if the clock changes or if the reset changes. There is no wait at the end, so this runs forever, over and over and over and over and over and over and over again. It has something called a variable in it. A variable is for a process. It's the same as a signal is kind of for an entire architecture, except it has some special properties. One of the properties is when you assign it, you use this particular assignment operator, called an equal. Now, second of all, very importantly, what this does is it asynchronously will change the register to 0. And this is a notation that says make all of the bits inside the register be a 0. Register has been defined up here as a new type, standard logic vector. And we give the indexes 3 down to 1 means it has the high order bit on the left, the low order bit on the right, and there's only 4 bits in it. We can make it 100 bits if we want, a single register. But in order to assign all of those at the same time, we simply say others are 0 and assign that to being the whole register, where others mean everything we didn't assign, which is everything. We're also assigning the output bit to a 0 by default if we reset the chip. If it's not a reset, we look to see if we had a clock event, and if the clock is currently a 1, meaning we saw a rising clock. If we did, we do this logic sequentially. And if you read this logic, you're going to notice that some of them are sequential assignments, and some of them are assignments to variables. Now, here's the part to ponder and think about. One of the things is I'm going to show you a different way to do the clock in another example in a minute. But more importantly right now with this is these that are assignments, the actual assignment does not occur until we leave the if block. So when I assign register and I sliced it to be only the bits 2 down to 0 to be the bits that were 3 down to 1, that doesn't really happen right now. That waits until the end to happen. Also, when I assign one that's a variable instead of a signal, it happens immediately. So this guy, work is immediately usable on this side. However, register, if you use it on this side, gets the old values until you get to the bottom and it gets recycled again. You would not write it this way, but this way works. And you might want to sit back and think about how could that possibly work and write it out as though everything changed and go, yeah, that doesn't work. And then write it out as though register being changed is actually deferred until we leave the if block. And then you'll go, oh, wow, if that really does work that way, it will work. So I just wanted to show you that, point you at it, and there's a test bench for it, and you can run the test bench. Nothing in here uses timing. However, in the test bench, we used 1 nanosecond. Leave that alone because we didn't put any propagation delay in it anywhere. And you'll be able to run it quicker without having to worry about anything. Because there's no timing changes in here and we didn't instantiate any of the other devices that need it. Okay, other than this piece of code, did you have any questions about anything we talked about in the first portion where we're talking about combinational logic? I'm taking a sip of coffee. I'm sneaking one while I wait for you. Ah, delicious. Okay, let me close some windows here. Now, you guys literally could write code. You could go to a job interview, and as long as it was combinational logic right now, and you had these examples, you would be able to write probably anything they would be asking you to do. I know you don't think you can, but the bulk of you can. Maybe there is somebody that can't, but you could be self-identifying. I'm not going to point you out. Okay, don't need that. Probably will need this, but probably just a different version is better. Okay. What is this? Oh, I know what that is. That's my little rumpus. Okay, so I'm thinking which of the two things I want to do next. Let's CD into the state directory. Do a directory when you get there. Now what is in here is 3 chips, a state D, a state JK, and a state T. All of them implement the same state machine. They are instantiated by this state test bed, or the test bench. The test bench will create an instance of each of these and pass them all values that make them go through their state. Basically, it's going to reset them and then keep clocking them. We can look at the test data to see if they worked. Now, interestingly enough with this, each of the states themselves are implemented in terms of a different flip-flop. This one obviously uses Ds, this one uses JKs, and this one uses Ts. We implemented those. Here's a D flip-flop, here's a T flip-flop, there's a JK flip-flop. So what I want to do is I want to look at each of those in turn and see where they're similar and see where they're different. So do this with me. Notepad D_FF.VHDL. Now, not surprisingly, it has an entity. The entity contains a clock, a clear, D, Q, and Q bar. Q bar is the same as a Q with a bar over the top of it, so it's the inverse of Q, which are the signals we're expecting to have on a D flip-flop. Now, the architecture describes it by creating a temporary Q hold variable in which we can save a variable, which helps us overcome that it doesn't change right now problem we just saw in that shift program. I'm not going to explain in great detail because it's a little more advanced than anything I'm going to be asking you on the test. And then we have a process and 2 statements. We have a statement here, and down at the very bottom we have another statement. These are concurrent statements. So this runs at the same time as the process, at the same time as the statement right here. And they don't stop running until there are no more changing signals. And if the signal changes, it kicks it all off again. The process uses a sensitivity list, and the 2 things that we might have change are clock and clear. If clear is a 1, we do an asynchronous set Q hold to a 0. Otherwise, and here's the other way to do a clock, we can simply use a macro that says, if we're on the rising edge of the clock signal, then assign D to Q hold. Otherwise, Q hold is simply still equal to Q hold. Now, you could use this as an example and write that if you had to. Now, how does Q hold get set? Well, out here, Q is constantly being set to whatever Q hold is. And down at the bottom, Q bar is constantly being set to whatever Q hold isn't. So this is a very good, solid implementation of a D flip-flop with an asynchronous clear. Anybody have any questions about this implementation? Okay, I'm going to push this to the back and we'll look at the T flip-flop. Do this with me. Okay, the ports are pretty much the same. The difference is instead of a D, it has a T. Well, yeah, I knew that. And its implementation will, of course, be different. However, we still set Q to Q hold, and we still set Q bar to not Q hold. We still do the clear the same way. We wait for clear to be a 1, and it was on the sensitivity list, so this process will be called if either the clock or the clear has changed. Doesn't care about the clock, it simply already sets Q hold to 0, because that's what a T flip-flop does, right? T flip-flop resets, sets it to 0. Otherwise, if it's the rising edge of the clock, we do what a T flip-flop does. If T is equal to 1, then Q hold is inverted. Otherwise, Q hold doesn't change. That's exactly what T does. It toggles when it's a 1. It does nothing otherwise. And this is, again, a very elegant solution an implementation of a T flip-flop. We put this in a piece of hardware, it would behave just like a T flip-flop with an asynchronous clear, just like the other one did. Notice also that we're using clear in a non-inverted way. We're making it become a 1 rather than a 0, which is a little different than it would be in real life, but we'll leave it that way. And that would, I think the reason that is because on a test one time I made that be one of the test questions, is convert this to an asynchronous clear. And there's more than just this, because you obviously have to change the test bench as well and the state machines so that they're sensitive to that. Let's look at a JK. Anybody have any questions about the T flip-flop? Well, you're pretty cool if you think that's cool, I can tell you that. Look at the JK flip-flop. It, of course, has two inputs, which are now J and K. It's going to, again, set Q and Q hold. It's going to set Q bar to not Q hold, and then have a process. This process is a little more complex because the JK flip-flop's a little more complex. First of all, if clear is set, we're going to set Q hold to 0, and it'll be handled outside. Otherwise, we're going to look for the rising edge of the clock, and then we're going to test our JK. If J and K are both zeros, no change occurs. Remember, when they're different, Q hold follows J. That's these two cases right here. The parentheses are necessary, okay, including the ones around the whole thing of the and here for the or. Else, if they're the change, do the toggle. So this describes very much, and remember, it's a description, it's not an implementation. It describes how the chip works. There is a thing we're going to change. Because this is a JK, and all our JKs are of the MS variety, we're going to change that word to falling. Because it should do its thing on the falling edge. Do that and say save. This is the JK flip-flop only. Okay, let's look at the state machine. We'll look at, first of all, state_d.vhdl. Now, what it does, it itself is going to be a chip, right? It's going to be a state machine chip. It's going to do that state machine as though that were the function we needed a chip to do. And it's going to have three inputs: clock, reset, and a vector of three outputs, meaning the thing produces three outputs. And those are the things that will be seen externally that will be twiddled with by the test bench. All three state machines will have these same signals. Now, how do we implement it if we're a D flip-flop? Well, we steal the input port for a D. We create some intermediate signals. And then we instantiate the three state bits we're going to need: state 2, state 1, and state 0. Where state 1 uses a D flip-flop, and we've port mapped that D flip-flop so that its clock is hooked to our clock, its clear is hooked to our reset, its D is hooked to our D2 signal, its Q is hooked to our Q2 signal, and its Q bar is hooked to our Q2 bar signal. And we do that for all three D flip-flops. Each one will be hooked to clock and reset, and the other three will be hooked to a different signal and a different Q, and Q bar, of course. Other than that, we then have to just simply put in the equations for the Ds. D2, which of course when it's changed will cause this flip-flop to do something, is equal to Q1. And this was derived from a Karnow map. D1 is affected by Q0, and D0 is affected by Q2 bar. Anytime these change, then they're going to affect one of our signals up here. And since they are wired to the Ds of these three flip-flops, each of the flip-flops in turn will call the underlying real D flip-flop to produce an answer on the next clock. But it's D, it'll be a rising clock. The outputs are exactly the same as the state names. We're very lucky. These could be individual equations. We could have more or less outputs, right? On a state machine, the number of outputs is not the same necessarily as the number of state register bits. But in this case, it is, and we're lucky because they're also exactly the same as the particular state we're using. So output 2 uses the Q2 we have as one of our signals. And the other two go to outputs. And remember, the outputs are way up here in our state machine's output. These three things are what the test bench sees. So it's only going to see the clock and the reset. It'll set those for us. But then it's only going to see changes to this. I made that lowercase. I made this uppercase. VHDL doesn't care. Okay, it probably should be the same. And I wasn't, when I wrote these, I don't want to change them all now, but when I was writing these, I wasn't worried about the naming convention for these because I knew I wanted to have a one-for-one correspondence. We would guess that the only thing that's really different if I do the state T VHDL is going to be everywhere I had a D, I'm going to put a T. And the equations will be different. And as a matter of fact, they're very different. A T flip-flop makes a very inefficient implementation for this particular state machine. Look at all these ands and ors and things we needed to have the T's be set. So it was fairly straightforward, which leads us to believe the JK may be pretty busy too. But surprisingly, again, state is JK. We have an extra port thing, so we're going to have some extra signals for the J's and K's. But down at the bottom, the equations are not that complicated. The only thing is we need 6 equations because we have J's and K's for each of the state bits. So I wouldn't look at this as being too complicated. So we can take and look at the test bench now. And it's called state_testbench.vhdl. It declares no inputs, outputs, as any good test bench should. And then it declares 3 components. It's going to instantiate a D, a JK, and a T. It's going to do all 3 of them at the same time. And here's the signals it's going to need. A clock and a reset. Remember, we're going to have a basic clock that we need to pass to all 3 of them. It's going to also have a output for each of the 3 D, JK, and T. And so to wire these up, the state machine for D, or state D, is instantiated. Remember, he internally is instantiating 3 D flip-flops. He's going to port map his clock to our clock, this guy here. His reset to our reset, right here. And his output, all 3 of them, remember this is a vector, are going to be set to our OD vector. Next guy will be the same, except his outputs go to the OJK, and he implemented a state JK, and he's going to do a T, is going to the OT. So once they have been instantiated, these are running constantly in parallel, and they're running in parallel with this process. We simply use a no sensitivity list process that sets the clock and reset, and then once it's set them, it just ticks the clock on and off, on and off, on and off. 1 per nanosecond. Since we didn't use any things that use timings internally, this is okay. We can leave it at 1 nanosecond for now. We're not going to worry about propagation delays in this example. So I should be able to just do it here to do a compile of everything. I don't want to go through and compile all that stuff. And as a last step, it took and created a timing diagram of the state_tb.vcd file, or into that. So I'm going to do gtkwave state_tb.vcd. I'll bring him over here. Now I'm going to put the clock on the top line. I'm going to put the reset on the second line. And then I'm going to put the OD, the OTK, and the OT. And I'll make it fit. Okay. Now, in doing what we've done, if we look at this, while we're reset, the outputs are all reset. By the way, if you have a registered thing like this, you can click on it and open it up and actually see the individual bits inside of it. So sometimes that's interesting to see as well. It also interprets the values over here, so you don't have to look inside if you don't want to. But the sequence seems to be 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, and then back to 0 again. So we have 6 states, and then we're back to 0. So we're not using all the states. And what it looks like is, think of these as LEDs. The right one comes on, then it kind of shifts and pulls one in, and then all 3 get pulled in, and then they start going out the left. The last one goes out the left, and then they're all done again. So it's kind of a little light pattern like you might use for a decoration or something like that. And if we just look at these lines without the opening, you'll notice that the JK is staggered by half a clock period, and it should be, because it happens on the falling clock. So we would not look on the rising clock at a JK, we'd look on the falling part in order to see the JK's values. But that's okay. Now the question that is begged here is what would happen if we accidentally, instead of initializing ourselves to zeros, initialized ourselves to one of those unknown states or unused states. And right now, we're using the states. Where is my cursor right now? Let me get away up here. We were using 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0, and we're back to 0 again. So it looks like we didn't use that, and we didn't use that. So what would be an interesting thing to think about is, how could we get the test bench to test that particular case doing what it's currently doing? And if we go to the, where is that? Yeah, state test bench, we see we don't have direct access to those. In this, we don't really have any way to get to that particular variable and make a change. Now, what we could do is we probably I'm trying to get to my desktop here. I'm digging. We might want to implement this. This is a D flip-flop with set. Remember how in a flip-flop, we've been having a clear only? There's nothing that says we couldn't add a set to the process list and to our inputs, and then instantiate this particular flip-flop so that set got called. And if it's set, we set the next Q to being a 1, not to being a 0. So this one implements not only an asynchronous clear, but it implements an asynchronous set. So interestingly, what that means is that if we had that particular file, let me go here for a second. If we had this file in this directory, then one of the things that we know we have is we have a JK state chip. Let's see if we can find JK state here easily. And in here, one of the things that we did is we implemented this component. But we could, in theory, implement this guy also. And he has an additional line, right? We had a set in here also. Which means, let's say we take the center one of these, and we instantiate him with set, and instead of making clear the reset, make it be a 0, meaning it's not asserted, and then make set be hooked reset. Something in that general neighborhood. Now, after rewiring, we might be able to, and I'm not sure, won't do everything for us. We need to GHD dash analyze, what I call the thing? JK flip-flop with set, something like that. Nope. What did I actually call those things? Oh. Actually, I did it in the wrong one. I'm not gonna bother finishing the exercise there. I should have done a D, not a JK. So when I changed this, well, actually, that's not hard, I don't think, to undo. It won't hurt you to see me make a mistake here. So he's just a JK flip-flop. He did that. Did I put him back the way I had him? With the one we really want to mess with. Is a D flip-flop. No, it's a state D. We're going to do the same sort of thing. Use with set. And he added a line here. The set. And we took the second one here and made this be the set. Now the question is, did I get everything? Because I did it twice, I may have not gotten everything. Well, do it shouldn't run correctly, so I needed to GHDL dash analyze. What do we call the thing? D flip-flop with set. I did what I tell you not to do. And then GHDL, we have to elaborate the state D. Analyze it first. What did I do? No, I can do it. I think everything will get done. Oh. Oh. Anybody, while I'm typing this, anybody tell me what I did wrong there? You look at the batch file, the first line in it clears out the library. I'll have to redo him. If this will run. It's something. If this didn't work, we will move on, and you can think about the ability to do a set in the middle of something and why that could be important. So we'll do the same thing we did. We'll do a clock, a reset. I only care about the D this time. Actually, let me pull one of the others over so you can see what the state should be. See what happened? Who wants to tell me what happened?
The second bit up for the D state machine is now a 1 instead of a 0 at the beginning.
Why does that break things?
Because that's not one of the states that we had programmed in the state machine, right?
Actually, that's quite true. Normally, what you would do is, if you didn't know, you'd program the state so that it went to a valid state if you accidentally had electrically gotten into the wrong state. So we're testing, we're electrically in the wrong state. Does it ever get back into this sequence? And looking across, it always goes to 101, who goes to 010, which are the two unknown states are pointing at each other. So this is an absolute bug in the design. We would find that only in the test bench. Again, this is a test question, sometimes on the final. And you'd only find this by running the test bench and realizing that if you get into one of those bad states, and we had to go through a little hoops there, it's usually a little smoother than that because I remember the right name. But we've proven that if we ever got in the wrong state, we never get back into a good one. So that was something I wanted you to see and at least appreciate. Okay, so I'm going to close some windows real quick. I want to do one other thing. Let's see. Get rid of these flip-flops out of the way. I must have a million windows open here. Look at me. I got back to the one that I did. I'm not going to worry too much. There's a couple left. Okay, let's assume for a second that we wanted to program a chip that did the majority function. Okay, the majority function, this is the, let's just do it for 3 bits. This is the A, B, and C of the truth table to produce Y, what we call the majority function. Okay, take and write out the values that go into this column. And the rule is, if there are 2 or more 1s turned on, there's a 1 in the output. So if most of the bits are 1, then we turn on the outputs. More interesting with 4, 5, 6 bits, but we'll do it with 3 just to show we know what we're doing. So go ahead and finish filling out that table. I will struggle with it myself over here. Let me grab a Carnot map. Okay, I'm going to label this. Who wants to tell me what the labels are on the left-hand side here?
Not A and A.
Okay. Who wants to tell me what goes above this? Somebody new. Somebody I haven't heard from tonight.
Not
Yeah?
B, not C.
Not B. Not C. Next column, somebody else.
Not B, C.
I get to do the next one. And who wants to do the last column?
B, not
B,
C.
not C.
Okay. Now we need to take our table over here and introduce it into the thing. 0, 0, 0, 1. 0, 0, 0, 1. 0, 1, 1, 1. 0, 1, 1, 1. Okay, I'm going to do some circling here. Obviously, those two get circled. And their name is going to be, see, A gets wiped out because both rows are used. So their name has to be the name of the column. So Y is equal to BC or this little chunk here. Who wants to tell me what that chunk's name is?
AC.
It's in the A row. And both of them are in a column that has a C at the top of it. Or, who wants to tell me the next one?
AB.
Okay, so the A row, that's these two guys right here. And the thing that doesn't change at the top is a B. Okay, so we need to remember this equation. I'll put it over here, out of sight, out of mind. Now do the following with me. Make a directory called COMB for combinational. Actually, you might have done that, but I think I'm going to do that somewhere else. Do this. CD up, CD up. No, actually, just stay in the work directory. Just stay in the work. Just one CD up. And in this directory, make a directory called COM, or combinational. If you made it down at the other place, doesn't matter. It just is more organized to put it with the combinational stuff. Now, in this directory, we currently have all this stuff. We're going to copy and2.vhdl to comb slash. Use a backslash, actually. Copy and to testbed.vhdl, COMB backslash. Now CD to that directory, CD to COMB. Do a directory. Should only have two files in there. We're going to rename them. Rename and_2.vhdl to comb.vhdl. Rename and to testbed.vhdl, comb_testbed.vhdl. Now this guy is ultimately going to execute that majority function for us. We're going to give it 3 bits and it's going to give us back a 0 or a 1 as an answer to tell us whether or not it is a majority combination. Everybody caught up? Give me a green light if you're caught up. Okay, So what we're going to do now is we're going to notepad. We're going to do the test bench first. com_tb.vhdl. Okay, now, the three places in here where, actually more than that because it's a test bed, we're going to replace everywhere it says and2 with COMB. Now, I think it's probably safe to do edit, replace. We'll try it. And you're going to replace the word and_2, replace that with COMB. Make sure you don't include the TB in it. Replace all. Now, it should have gone through the file and replaced everything that needs to be replaced in the test bed. So this is now that entity. This is the architecture of that. And we're going to use that component. Now, we know there's three inputs. So we have to add a C. Now, we have three. We're going to need 4 working signals, so add an S4. Just change this name from A2 to C2. I know it doesn't have 2 in, but actually you make it C3. C3 is a much nicer name. But that also means we have to assign in the port map that additional variable. So we have an A assigned to S1, a B assigned to S2. Now we need to have a C assigned to S3, and then Y gets assigned to S4. Now before we do any more, go up to the top, do a file save, so we don't lose our work. Now the next part is somewhat painful to do, so we're not going to do it all right now, and I'll show you how we're going to do it. First of all, what I'm going to do is I need 2 more lines that have X's on them inside. I'm sorry, 1 more line. I'm just going to copy the S2 line and make it here and change it to S3. So I have 3 things assigned to X. Now I'm going to do the same thing with the next one. I have 3 things. Make sure you change it to S3, assigned to 0. Then I'm going to delete the remaining test cases. Now, I'll show you what I'm going to do. Is I'm going to copy those 4 lines, Control C. Then I'm going to paste them back in 8 times. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Now I'm going to go down 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Now I've got valid test cases, and my test program is done. Now, if you only got a couple of these, make sure the tests you run, at least one of them is not a majority and the other one is a majority. But it's quite quick to do that if you just kind of go after it. And then when you're done, do a save. I'm going to go to my window here, and I'm going to do GHDL-S com_tb.vhdl. I'm just going to check the syntax, make sure I didn't type anything wrong. And mine passed. Remember, this is just the binary combinations of the numbers, so we use all 8 combinations. That's how I knew to make 8 copies. We really have 9 things here. One of them has X, and then there's the 8 values. So I'm going to park him off to the side for the moment. If you didn't get that done, you'll get it done after class, I'm sure. Let's notepad the other guy. Notepad comb.VHDL. Okay. The one thing we have to change in here is the name of the, well, we have the same problem. We have to change the and to thing. So you highlight that and you go up to edit, replace. Make sure you change the second one to COMB. Change that to COMB. Do a replace all. And we have a third input. We need to change that to a C. And in the architecture, we need to put that equation that we have squirreled away, which is here, into that area. So, let me see if I can get these both on the screen at the same time. So instead of what's here, get rid of the after nanosecond business also. We'll just write it as though we're going to run it, because I don't remember whether we use micro or nano in the output. I think we used micro, but we might not have. So I'm just going to write it exactly like it is for now. BC plus AC plus AB, semicolon. We know that's wrong. In the first place, we know that all the ands have to be put in parentheses to separate them. So I'm gonna put the opening parentheses in place and put my closing parentheses around it. And I'm going to put between them space and space. Now I'm going to replace the plus signs with space or space. I'll do a file save on that. Now this is purely synthesizable now because there's no timing in it at all. Let's actually put in some timing just so we're complete. After 22 nanoseconds. Let's take a peek at the other guy to make sure he, whoops, that's not him. Make sure he used he did use microseconds already, so he's fine. Okay, so your code should look exactly like mine now. We don't have a do it directory, so we have to do everything. So we're going to say GHDL, that's syntax check com.vhdl. VHDL syntax check testbed.vhdl. VHDL.analyze com.vhdl. VHDL analyze com testbed.vhdl. VHDL elaborate com.vhdl just com. HDL elaborate com testbed. HDL run testbed, putting the output in file vcd.vcd. Everything compiled, everything looked like it ran. We'll do a gtkwave of vcd.vcd. I'm going to highlight the component so I can extract the A, the B, the C, the Y. And I'm going to do a fit. And let's look and see if this is true. Anytime we have one bit turned on, so all X's, nothing should be on. Here we got all zeros, so it should not be a majority. We only have one turned on, so it should not be a majority. One turned on should not be. Next one should be. It is. Next one should not be. It's not. Next three should be. Should be. Should be. So we just designed from scratch combinational logic. We used some code that was pre-written, but we would have looked at it on a piece of paper and just typed it otherwise. So as long as we're careful with our cutting and pasting, bad habit, of course, to take any algorithmic code and cut and paste it. But when you're just taking basically the syntax, that's not such a bad deal. So we went through, we were able to do it. Flip-flops are not much harder. You can spend a little time looking at those as part of your studying. But the one that was called Shift 4, I would just look at it and kind of scratch my chin and say, I think he's going to come back to that on a different day. And I will. So I wouldn't spend a lot of your time trying to understand why that worked. But it did give you a good example of one that has variables in it. I think it's the only example I gave you. And they're not typically used for these smaller problems, and most state machines don't need them. You now have code, though, in that state machine code that we could write any state machine we wanted. We would just prune it down to a single type of flip-flop. Just keep that in mind if you're ever asked to build a counter. Okay, anybody have any final closing questions? I think we've eaten up most of the evening, and we've covered all the material I wanted to get done. Don't forget 6 o'clock on Friday if you want to come to a review session. I'll try to hold one if the school's Blackboard is up and everything's able to do it. Otherwise, we'll all gather on the Monday night. If for some reason on Monday night you get to try to connect and you can't connect, and it's not you just trying to hide out, double check the website because it uses a different ISP and see if I posted anything there or giving you alternate instructions. Otherwise, the test and maybe some more material will be covered on Monday night. We'll use up the entire class time, but I'm not quite sure how big a test I want to give you. And just in advance, all weekend keep telling yourself you're not going to cheat, you're not going to cheat, you're not going to cheat. Most people don't be reminded that, but invariably somebody gets tempted and somebody gets caught. So please don't be that person, and don't even think about trying to test that. Any but final questions or words? Some of you, next time I see you, it'll be test time. Some of you, I'll see you for the review. Make yourself a pizza or something before the review so you think you're having fun. Peter? No question, or did you just turn on your microphone? Anybody else? Okay, good night. I will see you guys either Friday at 6 or on Monday night at 6.